This is video 2, PowerPoint 2 of the structure of the atom. The first video we talked a lot about the main structure of an atom, its distribution of mass and charge, as well as isotopes and stability of said isotopes. This video is going to focus a lot more around the electrons, especially as we begin to cover 3.1 and 3.2, which is all about SPD notation and the shapes of these orbitals. So that's meant to be a little bit of a recap, but we'll need a blank periodic table. Let me grab one. There we go. Because I do need to give you a little bit of a lowdown of some bits, and this will become familiar to you, just switching over. This will become familiar to you in the next unit, which is all about the arrangement and trends of the periodic table, but it's a nice introduction as well. So from the first video, I talked about how these numbers, we have a larger number, which is the mass number, and the smaller number, which is the atomic number. This tells us the number of protons inside of an atom, also tells us the identity of an atom. So anything that has 11 protons is a sodium atom, anything with 33 is an arsenic atom, and so on and so forth. It also tells us how many electrons there are in an atom. So remember, in an atom, however many protons there are, we must have the same number of electrons. You may also remember this diagram, where we have the nucleus in the center with protons and neutrons, and then around the outside we have these rings or shells with electrons sitting in them. Now, in terms of how many electrons are surrounding the atom, as well as how many rings are surrounding the atom, we can get that information from the periodic table. Okay. So in this table, we have columns. Can't remember the word then. Columns going down. And we also have these rows, okay, going across. Now it is arranged this way due to a number of things. So number one is the group or the column. Okay, so going down a column, this is known as group. So all of these elements in the same column are part of the same group. And the group tells us how many electrons, and I'm using E minus to show electron, how many electrons are in the outermost shell. Okay, so how many electrons are in the outermost shell? So these are numbered. So we have group 1, group 2, then we've got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and then 18, or it can also be called 0. Now at GCSE, these are often excluded. Okay, so you would know the groups, or maybe remember the groups as 1, 2, 3, 4, 5, 6, 7, and 8. Okay, but when we include the transition metals, these metals here, we can put 13, 14, 15, 16, 17, and so on and so forth. Okay. So this tells us this group 1, it has 1 electron in their outer shell. These have 3 electrons in the outer shell, not 13, and I'll come onto that in a second. This group 6 or 16 has 6 electrons in the outermost shell. These have 8, these have 5, so on and so forth. And then in rows, these are known as periods. Okay. And period tells us how many shells are occupied. How many shells are occupied? Okay. So period 1, it only occupies the first shell. Period 2 occupies both 1 and 2. Period 3 occupies 3. Period 4 occupies 4, and so on and so forth. So from this, we can pick out any element, and we can find out how many electrons are in their outer shell and how many shells are occupied. So if we go for silicon, okay, so silicon has 14 electrons in total. Okay, it's in group 14, so it has 4 electrons in the outer shell, and it's in period 3. 1, 2, 3. So that means it has 3 shells. Okay. Now, as mentioned before, the second shell can only hold 2 electrons. And in this video, we're going to cover why. Okay, just keep that in mind. Now, the second shell, oops, let's go 1. First shell, we have 2. Second shell, we can hold 8. That's 1, 2, 3, 4, 5, 6, 7, 8. And then third shell is the outer shell, and that has 4. Oops. Third, 4. Okay. And if we add all them up, we should get 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now at GCSE, this is known as the 2-8-8 rule, which means that the first shell can only hold 2, second shell can only hold 8, and the third shell can hold 8. However, at GCSE, we don't understand why the first shell only has 2. And we also lie. The third shell not only holds 8, but it can hold a total of 18. And the fourth shell can hold 32. Why? That's what we're going to cover today. Just switching back. There we go. So that's just a little bit about, there we go. That's fine. That's not true. Yep, there we go. So the third shell can hold 18 and the fourth 32. Let's explore why. Reason for this is because of something called subshells and orbitals. Okay. First, I'm going to have to give you some definitions. So, the rings or the shells has an actual definition, and it's not quite this is where electrons live. No. The official definition of an electron shell is a group of atomic orbitals with the same energy level, and this will become clearer as we go on. But shells are made up of subshells, and each shell has what we call an orbital. Switching back. So, according to Bohr's model, a model that we are all familiar with, electrons sit in shells, and typically they are depicted as sitting on these rings relatively nicely. In reality, electrons do not simply sit on these shells around the nucleus. If you remember the video that I showed you last week, last session, you remember that the lady said that these zoom around empty space around the nucleus, and that is true. The reality is, unless we know the direction and the speed of an electron, we cannot with certainty say that the electron lives there. We cannot pinpoint it. We cannot drop a pin and say, right, it's there. Instead, we have to go into a little bit of maths, and we have to say, right, we don't know which direction it is because it's whizzing in any singular direction, and we don't quite know its speed because it can speed up, it can slow down. So here we have this area where we know that there are 2 electrons within this space, but we cannot pinpoint it. That's what an orbital is. An orbital is this probability, this space, which says 2 electrons live here. So we cannot know exactly where an electron is at any given time unless we know the direction and its speed. So because we don't know those 2 things at any given time unless we experiment, we have to go with probability. We have to say, right, somewhere in this space is 2 electrons. And that's where our orbitals come in. So, first shell. Now, as mentioned, shells are made up of subshells. Okay. And in terms of subshells, there are 4 different subshells. We have S, P, D, and F. We're not going to be talking a lot about F, okay? But those are the 4. And within each of these subshells, there are, orbitals. And remember, an orbital is a region of space where 2 electrons are sitting, are found. It's where they live, basically. Okay. Now, depending on which energy level you're looking at, I'm just going to scribble out, depending on what energy level you are looking at, will depend on how many subshells we have and therefore how many orbitals we have. So going back to the first shell, okay, well, I've just told you that the first shell, the orbitals tell us where 2 electrons are. And I've been telling you that the first shell can only hold 2 electrons. This must mean that the first shell only has 1 orbital. Now that orbital is in the lowest subshell. It's kind of like it's somewhere in there, which is S. So in the first shell, we have an S orbital, an S subshell, which is spherical. It's a ball. It's a football, it's a cricket ball, that kind of thing. It's 3D space, it is a sphere. And somewhere in there we have 2 electrons. And that is all the first shell has. The first shell only has 1 subshell, S, and S only ever has 1 orbital where you can find 2 electrons. It is the lowest energy subshell and orbital there is in terms of atoms. Now, within this, we also have to consider, we're thinking 3D, aren't we? We're talking about regions. If we're talking about 3D and we're talking about regions, we need some sort of axis. Well, you may remember X, Y, and Z. You know, on a graph, typically you have Y and the X axis. The one that's not depicted is Z, so Z comes straight up. Yeah, if I put my pen there, that is Z going up here. That's Y, that's X, that's Z. You can use your fingers as well. Ooh. There we go. Yeah, Y, X, Z. So we're thinking about 3D space. So if you were to put our sphere onto our axis, well, it encompasses all axes, doesn't it? There's no one direction in which we can say, oh yeah, it's going up the y-axis. No, it's a ball. It encompasses all three. When it comes to the next energy level, number 2, then we start to relate to these X, Y, and Z. Okay, so number 2, second shell. Now, second shell, as mentioned, can hold 8 electrons. Okay, it can hold 8 electrons. That is still true. And the second shell contains 2 different subshells. One of them is an S, and the other one is P. P, I remember it as peanut. At A level, they prefer you to call it a dumbbell shape. But when I was at university, my professor called it a peanut, so I'm sticking with peanut. And essentially, to get from here to here, probability is halved. So instead of it being this circle, we split it. So it's kind of like this. It is literally like a peanut with its casing still on. Okay, and because it's a little bit more elongated, when we begin to apply it onto our axes, we begin to see that actually now it's beginning to make a bit more sense. Okay, so this one that I've just drawn, this is lying across this axis here. Let me put my pen there, like that. See? So that's that orbital. But we still have 2 other vectors. We still have that one and that one. So yes, within the P subshell, and I know it's very difficult to draw, but that is going that way. That is X. That's going up. That is P. And that is kind of going diagonal, so that is Z. We can have 3 possible regions where we can find 2 electrons. Yeah? So we have 3 orbitals in the P subshell, meaning that in the P subshell, we can have a total of 6 electrons. Yeah? So we have 2 in here somewhere. There's 2 in here somewhere, 2 in here. So in order to make the second shell, we need to have 2 subshells, S and P. S can hold a maximum of 2, P can hold a maximum of 6, lying across all 3 vectors, all 3 directions. Finally, coming on to the third subshell. The third shell. Okay. So the third shell still has an S. It still has a P. But how many electrons in total can the third shell hold? It can hold 18 in total. Well, S and P only make up 10. Sorry, 8. Which means we are missing 10. That's where the d orbital comes along. So with d, we have again sliced. And it's kind of like a clover. That is what A level wants you to mention. I call it a daisy. And I cannot spell. Welcome to my TED Talk. It's a daisy. So it does look like a four-leaf clover. That is a horrible drawing. It can still lie on the axis, so we can still have it in the direction of X, we can have it in the direction of P, we can have it in the direction of Z. We can also have it in between the vectors, so going X, Y. And there is a fifth magical one, which looks like a P orbital with a life jacket around it. Just to make things more complicated. Luckily for you at this level, you do not need to know what they all are. You just need to be able to describe them, and you can describe them as a daisy or as a p orbital with a donut around it. But because of this, because of the presence of these and how it can lay in the regions, you can have 5 orbitals. Each of these can hold 2 electrons. So yes, even in our four-leaf clover, we will only ever find 2. So they could be in those 2, it could be in those 2, could be in these 2, could be in those 2, yeah, could be anywhere. Anywhere within that clover space. So this means that the D can hold 10 electrons. So with the 10, plus the 6, that's 16, plus 2, that's 18. Now in the PowerPoint I do mention the 4th shell. You don't need to know about the 4th shell because in the criteria it only asks for S, P and D. However, might as well cover it just so that you are aware of it. So 4th shell has S, P, D and another one called F. F stands for flower. So it does look like a flower. Looks like a mess. Anyway, but within the F, it can hold 7. 1, 2, 3, 4, 5, 6, 7. It can have 7 orbitals, each of which can hold 2 electrons, so that gives a total of 14. So if we have 14 plus 10, that's 24, plus 6, that's 30, plus 2, that's 32. Okay. Now, for your assignment, you will need to know about SPD notation, especially when we begin to come on to the next set of slides, which is ionization energy. Okay, so just coming back to our periodic table. we can begin to add a little bit more depth into our periodic table. What I mean by that is the group tells us how many electrons there are in the outermost shell. The period tells us how many shells are occupied. Also, depending on where you are looking, we can split this into blocks, which can tell us where the outermost shell, where the outermost electron is sitting. So we can figure out if the outermost electron is sat in S, P, D, or F, depending on the blocks. And this is what it looks like. So the first two groups here, this is called S block. So their last electron in all of these sit inside of an S orbital or an S subshell. Over on this side, this is the P block. So out of all of these, including the new ones that are down here that is not printed on these, it says UUQ, but they have been named now. Sidetrack. If you pick or look at any of these, the last electron will sit in a P orbital. Within the transition metals, the last electron sits in a D orbital. And in the actinides and the lanthanides, these sit in an F orbital. How can we prove it? Well, first, I'm going to have to rack your brain a little bit more. Right. So I'm going to have to introduce you to something called a spin diagram. Now for this unit, you do not have to complete a spin diagram. However, it's definitely going to help you understand where notation comes from. Electronic configuration comes from. So, spin diagram, it shows us the energy of the orbitals within the shells. Okay. So, looking at the first, here we go. So, looking at the first shell, we know it only has an S orbital, which is, an S subshell, which contains one orbital. So, first shell, number 1, we're just going to show it as a line. So that line represents one orbital. So that's an S. Yeah. So first energy level, S subshell, we have an orbital. Moving on into the second, number 2. We still have the S, but we also have P. And P's are slightly higher in energy. Not much, but slightly. And there's 3 of those, yeah? 1, 2, 3. In the third shell, we still have an S, which still only has 1. We still have a P, which has 3 orbitals. And we also have the D, which contains 5 orbitals. And again, that is slightly higher in energy than the previous 2. I'm not going to cover 4, okay, because that's where things get a bit complicated. But instead of depicting our atoms like this, we begin to move on to something called SPD notation. So if we go back to our example of, there it is, silicon, yeah? It's 14, so we have 2 here, 8, and then 4 around the outer shell. And I said, right, so the GCSE electrical configuration of this is 2, 8, 4. Now we're moving on into A level. We don't simply put numbers. That doesn't tell us a lot about the electrons. Using this method tells us exactly what energy level, what subshell, and which orbital that electron is sitting in. Okay. Now there are a couple rules which you can begin to look into if you wish. It's handy to be aware of them. Okay. So the 3 rules are Aufbau principle, Hund's rule, and Pauli principle. Okay. Essentially, these are the 3 rules which tells us that, so from Pauli, that no 2 electrons can occupy the same space. Hund's rule is that the lowest occupied energy level must be singularly placed before we pair them. And Aufbau is that we fill it in from lowest energy to top energy. Okay. Typically, if you do go into this, you may see electrons be shown like this with 2 arrows. Okay. Instead of E, and all that kind of stuff, we use arrows to show Pauli that no 2 electrons are the same. And that applies to his rule. There's also a spin up and spin down because of repulsion, but you don't need to know that at this level. Just know that this represents 1 electron, this represents a second electron. So starting at the very bottom, 1, 2. In our first shell, we have 2 electrons. Yeah. Second, 1, 2, 3, 4, 5, 6, 7, 8. In the second shell, we have 1, 2, 3, 4, 5, 6, 7, 8. Yes. Now we have a total of 14. How many have we used so far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've used 10 so far, so we've got 4 left over. 1. The P's higher in energy. I still have to stick to the S. 2. 3. And 4. The reason why I've done this is because of Hund's rule. But that's a bit of extra. But from this, we can begin to list or understand the notation. Okay? Which is this. So for the electron configuration of silicon is 1, first energy level, S, in the subshell S, we have 2 electrons. Moving on up in energy, in the second shell, in the S subshell, we have 2 electrons. In the second shell, in the P subshell, we have 6 electrons. In the third shell, the S subshell, we have 2 electrons. In the third shell, in the P subshell, we have 1, 2. Now, what did I say about the blocks? I said, depending on where the element is placed in the periodic table, wherever its position is in the periodic table, it will tell us how many electrons are in the outermost shell, how many shells are occupied, and which block that outermost electron is sitting on. It's occupying the third energy level, 3. We need to look at block P. So 3, block P, and it has 2 electrons. 1, 2. Silicon. And it begins to look like a little bit like coordinates as well. So for example, this is just showing off now. Let's take a look at D block. We'll go that one. Okay. Palladium, PD. Its outermost electron is in D block. It occupies the 4th shell. I know it says 5 there. There's a reason for that. I'm saying 4. And it has 1, 2, 3, 4, 5, 6, 7, 8. So its very last, this bit, the very last bit would be 4D8. And you can check that on Google. Boosh. Anyway. Yeah, but you can apply this to any of the periodic table. So hydrogen is 1s1, 1s2, 1s2, 2s1, 1s2, 2s2, 1 p d d d d, and so on and so forth. Okay. So to summarize, oops, there we go. So to summarize, this is an electron shell. So this that we're showing is shell 3. In an electron shell, there is a group of atomic orbitals with the same energy. within the shell there is a subshell, which is a group of orbitals with the same type within a shell. And then we have an orbital, which is a region within an atom that can hold up to 2 electrons with opposite spin. Oh no. Yeah, that's right. And that is everything for session 2, all about the electrons and SPD.